You can read that section. It has its verbiage and how it wants to talk about it, okay, in the way the textbook does. I'm just going to explain to you how it makes sense to me, okay, in my own words. And so use both of those to make sure you guys understand what's going on here. So let's say if we have a molecule, let's say a alkyne, and we want to treat it with this sodium amide here, or this amide here where we have the negative charge, okay? And we want it to react in this manner. We want this to come, grab the proton, and form this. We want to form that anion plus ammonia. Like that. That's what we want to have happen. But reactions don't just happen as in solid states. Typically when we're doing organic reaction, it's going to be in a solvent. So we have to ask ourselves, what solvent do we use? Do we use an organic solvent like hexanes or benzene? Well, we don't use benzene too much anymore because it causes cancer, but back in the day, okay? Or do you use a polar protic solvent like water or methanol? That's the question that we have to ask ourselves. So let's say we want to use water as our solvent. Okay, that's our solvent. We have to ask ourselves a very simple question. Will our species or our reactants, particularly the ones that act as a base or a nucleophile, which you'll learn what that means shortly, but the thing that has the negative charge, okay? Because what do we want that nitrogen species to do? We want it to react with the alkyne. That's what we want to have happen. But this reaction is in a solvent. So you have to ask the question, does that nitrogen species react with my solvent? Because in order to do a good and proficient chemical reaction, your solvent is just there. It's inert. Your reactants should not react with it. If your reagents do react with the solvent, then it's a horrible solvent. Because if water's a bad solvent, let's say, this nitrogen species isn't going to react with that hydrogen. It's going to come and react with these hydrogens on the water. So in order to answer that question, we have to do an equilibrium thought experiment, more or less. What we're going to do is we'll take our nitrogen species and react it with water. And we will do an acid-base analysis. And then we are going to predict equilibrium. So what's going to happen if I take that nitrogen species and put it into water? Well, we're going to have an acid-base reaction where we will generate NH3, and then we would generate hydroxide, just like that. So does this reaction occur? Is the question that we want to ask ourselves. So in order to answer that, we need to predict equilibrium. So if equilibrium is favored to the right, we can say that the reaction is reacting to the products. So if it's favored to the right, then that means the nitrogen is reacting with the water. And that is a horrible solvent to choose because it's reacting with the water. However, if equilibrium is favored to the left, then there's really no reaction that's occurring to a significant amount, and water would be a wonderful solvent choice because it's not going to react with water because it's favored to the reactant side. Does that make sense? The logic behind that? Okay, now we just have to answer the question. Which side is favored at equilibrium? So what are we supposed to do? What's our first step?
Octet rule?
Octet rule? No, not the octet rule. What did I do with equilibrium last time we were in class? What was the first step?
Compare the pKa's of the water.
Okay, even before that. Find your acid. Okay? That's our conjugate base. We got to go through this analysis. That's our base, like that. Okay? And then what's step 2 to predict which side equilibrium's on?
Use the PKA.
pKa, so the pKa of water is what?
15.7.
Okay, so we'll just say 16
Amine is 38.
and about 38. Okay. Now that you have the numbers class, which side is favored at equilibrium?
The right.
Why?
Because the pKa of the water is lower than the amine.
Okay, so said another way, we're trying to find the weaker or stronger acid. We're trying to find the weaker acid. Equilibrium is favored towards the weaker acid. So at equilibrium, we could draw it more like that. You know, big arrow to the right, small arrow to the left. So based off of that analysis, is water a good solvent choice? No, because it's reacting with our reagent. So by how many orders of magnitude is it favored to the right? What's 38 minus 16? 38 minus 22? Is it 22 times to the right? No, it's 10 raised to the 22. So when we have a difference, when we compare two answers, when we have a difference that's greater than 3, okay, greater or equal to 3, we say that this reaction is irreversible. Which is saying, hey, it's going all to the right, and very little to none is coming back. Okay? So that's irreversible. However, when you do a reaction where it's less than 3, the reaction is going to be reversible. So if you want to know if a reaction is going to be a strong reaction either to the products or the reactants, you do this acid-base analysis and figure out which side is favored. And then you look at the magnitude. If the magnitude is greater than 3, either direction, left or right, it's favored in that direction irreversibly, typically. And then if it's 3 or less, then it's reversible. All right? So it's a good rule of thumb. So we would want to have a reaction, a good solvent. What would a good solvent look like? Equilibrium is favored to the left irreversibly. All right? And so if you guys do this, I'll leave this to you guys. I'll tell you that hexane would be a wonderful solvent choice. Because what does hexane look like? It has 1, 2, 3, 4, 5. It has 6 carbons. That would be a great solvent. Because what's the pKa of one of these hydrogens? 50. Right? Now you do that analysis with hexane and you'll see that equilibrium would be favored to the reactant side. So that's the leveling effect. Does your reagents react with the solvent? How do you figure that out? You do an acid-base analysis, figure out which side is favored at equilibrium. Now, when you read the textbook, it's going to say something like this. The base cannot be stronger than the conjugate base of the solvent. And you're like, what? So you take my explanation. I've identified the conjugate bases and whatnot, and you can piece the verbiage in your textbook together. So it's going to take some thought and some critical thinking, because I explained it very straightforward and simple. The textbook adds a little bit more vocabulary to it, and you need to know that. Okay, so 3.7. Make sure you understand what the leveling effect is. When you continue to go through the sections here of your textbook, I need you guys to, I'm not going to talk about it because it's just review from general chemistry. You need to know your definitions of Lewis acids and Lewis bases, how they differ from Bronsted-Lowry acids and bases. But don't get so caught up on definitions and definitions only. It goes back to my analogy of the bicycle. You want to learn how to ride a bike? You read books, you watch YouTube videos, but you never get on the freaking bike. And so that's the lower bloom in Bloom's taxonomy. It's just a freaking definition.